not responds.
There we go.
Oh, Graham. That's what it is.
My computer doesn't want to come back from spring break here.
He's like, okay.
Oh my gosh, come on.
It was for everybody that was originally getting paid. It was the startup pay too. So it was just like a yeah, it was like an entire. I'll take it. You know, yeah, $2 extra. Pretty awesome. And then I still have my ability to get a raise this month. So like if I get a good review, I can get an injury. So I get like $11.25 or something. Only part-time, so I
Okay, welcome back. Hope you all had a good spring break. Yeah? Okay. Don't remember where you are, what we're doing. Okay, so I'll hand these exams back at the end of class so that you can focus on getting yourself going again. The average on the test was a 70.4, and then the first exam, the average was a 77. So the average went down. Our standard deviation is about the same. That just tells you how spread apart the grades are. So a large standard deviation means the grades are kind of spread out. If you have a small standard deviation, everyone's kind of close together. A 19-point standard deviation is pretty high, but not, I mean, I've seen worse. I like it to be about 15. That's normally where I see it, but it's 19 for this test. So there's a lower average and a higher spread of grades compared to the first exam. 4 A's, 4 B's, 7 C's, 4 D's, 6 F's. And then this chart shows the orange is the exam 2 grades, and they are listed from highest to lowest. So the highest score on exam 2 was a 105. The lowest score was a 21.7. And then what you can see is the blue one is the exam 1 grade. So for example, the student who got the highest grade on this test actually did not get the highest grade on the first test. So they went up. And then the student who got the 102 actually had a 107, so they came down a little bit. So you can see kind of, you know, the only real big changes I see are like this one here, you know. This is actually good. This is an improvement, but it's still not quite there. This is actually danger zone here, right? Because, yeah. So you can make the best sense out of this, right? Yes?
In your opinion, based on the questions given on the exam, what sort of grade on it do you think shows comprehension of the work?
70-ish. Yeah.
So as long as you got like around 70.
Yeah, I mean, I think we kind of lose sight of what letter grades mean in college. Everyone wants to get the 4.0, everyone wants perfect grades, but you have to remember what it means, what each letter grade is supposed to represent. So, you know, a C is average. That's what it means. A C student is an average student. You know, a B student is above average, and an A student is exceptional. And we all know in the real world, not everybody can be exceptional, right? So it would, well, we're all exceptional in our own way. You know what I mean? So, you know what I'm saying, right? So I think if you're hovering in the C range, you know, it's nothing to feel terrible about. I mean, if that's where you are, it's, of course, everyone wants to be on the high end, but, you know, can't always have everyone over there. I wouldn't mind giving everyone hundreds. I mean, the material's the material. If everyone did exceptionally well on it, then I would say that everyone gets A's, whatever. Yes.
Did you give us a curve?
I don't remember. I graded this before. What's that?
On Canvas, I have a different grade when I checked.
Is it higher? Oh, that was the problem that you turned in. Remember that problem you turned in?
Okay.
Yeah, I added that to it. Yeah. So, yeah. Anything else?
You added that to his test, you're saying? The problem that he turned in?
There was a problem. Yeah, but
was
he.
fine? Oh, that was.
No, he just wanted a problem, and I gave him a problem. Right. That was. I don't think anyone else turned that in, but he came into my office and talked to me about it. So, I mean, that's anyone who wants to come in and talk to me and says, "Hey, give me a problem." I'm happy to provide you with a challenge problem, and if you can do it, then I don't mind giving you some bonus. But now everyone's going to come into my office. Which I don't mind. That's fine with me, but just don't show up and be like, hey, I'm here for the bonus problem, you know? Like, okay. All right, so, I mean, that's where we are, and now I was required to post midterm grades. Not post midterm grades, but they have an alert system or something that we have to do, and I filled it out last night. And anybody who I believe was below a 60 average for everything you've done up to this point, the system automatically generated an email, I believe, and it's just going to tell you like, hey, it might say contact your professor. I mean, I don't know what it says actually, but just to know, it's an automated thing. It's not. I didn't sit there and like look you up and type an email to you. It's just a warning, you know, like, hey, look, you know, we're halfway through and you're not passing and it's not looking good. So talk to your professor about where you stand. I mean, at this point, unless you have like a 20 average in here, you know, you could still theoretically recover from pretty much anywhere where you are right now, because about half the grade is gone, about half the grade is still out there. But you'd need to do well. And then on the other end, if you're like cruising here on this end, you know, you can drop. So we don't want to take our foot off the gas. All right. Anything else? Did I answer your question? Okay. All right. Well, we get to continue what we were doing before spring break, which I barely remember what it was. But it's related rates, and we had finished, maybe this will kind of get things going there. We had done the cone problem where we were trying to fill up this cone with liquid, and we were trying to figure out how fast it was coming up, how fast the height was changing at a certain particular point in time. And to do that problem, we had to like cut this cone in half and then look at it like triangles and do similar triangles. Does that sound familiar? Yeah. Okay, so we're going to look at, I believe this is going to be the last problem. Well, we might do the latter problem. Let's see how fast we can get through this. This one, this is actually the problem that I gave you, right, Hugo? Not this exact problem, right?
Similar.
It was similar to this problem. We did the one out of the book. So, all right. We have a runner, all right? Let's try and get an idea what's going on with this problem. A runner sprints around a circular track which has a radius of 50 meters. She runs at a constant rate of 7 meters per second. I think that's pretty fast. Well, she's very fast. She's exceptional.
7 meters.
Okay. Her friend is standing at a point 100 meters away from the center of the track. How fast is the distance between the two changing when the two are exactly 120 meters apart? All right, so can you visualize what's happening here? You have a circular track. I'm just going to draw a quick picture here. Circular track, and you've got this person that's running around this track, right? It doesn't say clockwise or counterclockwise, right? It just says that they're running around the track. So what do you want to go, clockwise or counterclockwise? Clockwise? Okay. So this runner is going around the track like this, all right? All right, so we got this runner, and then you have radius of this track. It's a circle, so the radius here is 50 meters, right? And then you have a friend that is standing at a point 100 meters from the center of the track. So that could be 100 meters, could be out here or 100 meters any direction, right? So let's put the friend. Let's orient the friend kind of in a natural way. Like, let's not put it up here. Let's just go straight out to the right, okay? And just imagine coming out like this. And put the friend there, and just remember that that's 100 meters. All right, these are meters. And let me highlight where the person is a little bit here. Here's our person right here. Now that blue dot's moving, right? So it says, how fast is the distance between the two changing? So I need to somehow illustrate the distance between the two. So I should probably connect the two with a straight line. Sound good? Okay, if I connect these two with a straight line, like this, then that red line is changing also, right? As the person runs around the track. What'll happen if this person's right here right now and they start running, right? Then this is going to shrink. And then when they get to here, how long is that red piece going to be? 50. And then it's going to start getting longer. And when they're on the opposite side, how long is that red line? It's going to be 50, 50. All right, so 150. So it says, how fast is the distance between the two changing when the two are exactly 120 meters apart? So when does that happen? 120 meters. It's going to happen in two places, isn't it? Somewhere down here and somewhere up here. Yes? And for us, it really doesn't matter which one. In one case, let's say this one right here, somewhere around here it's 120 meters. That distance would be growing, wouldn't it? Because they're running around the track like this. But when they come up here, that distance would actually be shrinking. All right. But what we want to know is how fast it's changing, whether or not it's growing or shrinking. And I kind of talked about this one of the last classes that we had, that when it comes to related rates, it's relative. I think I was going to throw something towards you. And I was saying, like, I could look at that as positive in my direction, or you could look at it as positive. It's all about, it's relative to the observer, if you want to call this direction positive or negative. So all that matters to us is the rate at which it's changing. Whether or not it's positive or negative, that just means growing or shrinking. Okay? Y'all okay with this? All right. Now, I have an animation that's kind of a better illustration of what's happening. Ah, it's counterclockwise, sorry. Well, you know what? I could run it backwards. Can't I? There we go. Okay, so there we go. We've got this runner running around the track very fast. That's very fast. And so it's green on this one, but you can see it's growing, and then it's going to shrink, right? And we want to know at a specific instant in time how fast that green thing is growing or shrinking. Now, I'm gonna actually snap to the instant in question, and there it is right there. All right? That's exactly at the moment that this is 120. At that moment, how fast was that green shrinking? Understand? All right. So we get to set this thing up. So the way that I was kind of helping you, and I believe, if I remember correctly, I think a lot of you did pretty well on the related rate problem on the test. I think. I gave you 2 of them, right? You got to choose one? I don't remember. I graded that like right after y'all took it. So, okay, we have the general. I'm going to draw a general picture, right? Let's get this general picture set up first. I'm not going to place my runner 120 away, right? I'm just going to place that runner arbitrarily somewhere. So let's place the runner here, and then let's come out like this. There's the other person. And then here's my thing I'm interested in. Now, on that general picture, can I fix any of these things to be constants?
Radius.
The radius is constant, so this is 50 no matter what, right? And isn't this distance 100?
Yes.
That's definitely not going to change. The only thing that's really changing there is that red piece. So let's call it, I don't know, R? I don't care. You can call it whatever you want. R. All right? You could call it X, Y, Z. I don't recommend calling it D though, little d. And the reason is, remember we're going to do something like, we're going to want to know what dRdt is here, right? And if you use little d, it looks like this, dd, dt. It's just weird. I don't know. So I avoid using little d, even though you could. All right, okay with that? All right, let's just leave that as that for now. And let's look at the instant, is that what I called it? Instant, or the moment in time? Now at the particular specific instant in time, we know we're over here. We know that's 50. We know this is 100 still. But now we know that this is 120, right? That's our picture at the instant in time. So R is 120. Let's put what we're given and what we want. So what are we given? And what do we want? Maybe either one. What? D what? dV/dt?
Velocity.
We're given the speed of the runner, aren't we? Okay. But you said dV/dt, but I don't have a V anywhere on my picture yet.
dRdt.
Okay, let's get to that. What about what we want, though? What do we want in the problem? dRdt. We want to know the rate at which the length of R is changing with respect to time. We want that at what moment? At what exact moment do we want that? At R is 120 meters, right? We still have not determined what we've been given and how we're going to connect that to this variable R, right? We still have not done that. And there's kind of a problem, an issue here, because we only have one variable in our picture, right? In our general picture. That's the only thing we have. So let's start talking about that speed. Let me get this off of here. Let's talk about the speed of the runner. What was the speed of the runner? 7 meters per second? Okay, the runner's speed is 7 meters per second. How can we use that? How can we use that piece of information? Now this goes back to pre-cal. Think about the runner going along here. They're running along a curve, aren't they? Okay, they're running along a curve. 7 meters per second is a linear speed. It's a linear speed. So there's something from pre-cal that has to do with circles and linear speed. Let's see if you remember any of that. Angular speed, okay, right? Angular speed. There was angular speed in pre-cal. There's linear speed. But let's try and think about it a kind of a different way. I like to do it this way. So look, we have a circle, right? This circle has a radius of 50. Can you tell me how long it's going to take that person to run one lap? How long, time-wise? You have to figure out the circumference of the circle, don't you? And then once you find it, let's just say for the sake of simplification, let's say that the circumference of this was 700 meters. How long would it take this person to go around? Well, 700 meters, they're running 7 meters per second, so it'd take 100 seconds, wouldn't it? Make sense? So let's find the circumference of this. The circumference is 2 pi r, right? 2 pi r, not this r, right? just 2 pi times the radius. The radius of this is 50, so what do we have, 100 pi? That's the circumference of this? Now, how does that help me?
You can time how long it takes the.
Okay, so how long will it take the runner? Let's see. It takes runner, how long? How long does it take the runner to go around one time? What's the calculation I have to do? 100 pi divided by 7, right? 100 pi divided by 7. That is the circumference of the circle divided by the speed, right? I can travel, this person can travel 7 meters in 1 second, and I have to go 100 times pi meters, right? So if you wanted to, you could do, it's 100 pi meters over meters per second. And if you flip this up, put seconds up here and meters down here and get rid of that, then the meters cancel, and this is going to be 100 pi over 7 seconds. 100 pi over 7 seconds. That's how long it takes the person to go around, right? Now why, I still haven't alluded, you know, like where we're going with this,
We
yes?
did the factor label method and just added in the value, not the values, but the units, and then.
I do what?
You like factor label method?
I guess so. Sounds like a chemistry term. Okay, that I still don't see how that's helping. I gave you this as like try and lead you into the right path here, but how is that going to help me get this given? I'm given the linear speed, right? I'm given the linear speed of the runner, and somehow I've done this, and all this tells you is how long it takes a person to run 1 lap. Right? That's the time it takes. We need another variable in our picture. We need something else in this picture. Can you label anything in this picture that is going to change as this situation unfolds?
The position of the runner.
This position?
That position will change.
Yes, it changes
7 meters a second.
at 7 meters per second. But I'm asking you to give me another variable in the picture that we don't have here that's changing. Yes.
Hold on. Can you put theta in there?
Theta where?
In the angle, in the inside the circle?
Here. This right here, if we call this theta, then theta is changing, isn't it? How fast is theta changing? Well, 100 pi over 7 seconds is how long it takes to go what? 1 lap around. Okay, so this is where the pre-cal part comes in. We have taken the speed of the runner to figure out how long it takes to go 1 circle, 1 revolution, right? And now I'm going to use that to get what's called the angular speed. Angular speed from pre-cal is the angle over the time. It's how far you go, right? How much angle you turn through divided by how much time it takes you to do it. So what is the angle that we go through in 1 full revolution? In 1 full revolution. 2 pi, right? So our angular speed is 2 pi, that's 1 full revolution, over the time it takes me to do 1 revolution, which is 100 pi over 7. Let's see. Does that make sense? We've converted linear speed to angular speed. That's all we've done. You're running around this track at a certain speed. Okay, well, how fast is your angle changing? If you're running at a constant rate, then your angle's changing at a constant rate, isn't it? So this is going to be what that rate is. So let's clean this up. This is the same as 2 pi over 1 times 7 over 100 pi. So all I did was like flipped it, right? And then the pi's cancel, and you get 14 over 100, which reduces to be 7 over 50.
Would there have been a measurement over there with either, that would have been still being meters, right?
No, it's an angular measurement, so it's radians.
Okay.
Okay? This is going to be radians per what?
Per second.
Per second. All right, so final result here is that we get 7 over 50 radians per second. That's the rate at which this angle is changing. Every second, it changes by 7 over 50. Someone on their calculator do that. 7 divided by 50? Not all at one time, please. All right. Guess you all had a good spring break. This is approximately 0.14? I'm just doing this to try and help you see something. Radians per second. All right. Now, let's do this 100 pi over 7. Let's figure out how many seconds this is about. So 100 pi divided by 7. About 44.9. 44.9 seconds. Okay? What this is saying is it would take this person about 44.9 seconds to run around this track. The angle is changing at 0.14 radians every second. If I multiply this times this, what do I get? Let's see. $6.28? About 6.28? What is 6.28? 2 pi. So in terms of radians, remember radian, pi is halfway, 2 pi is all the way around, right? But pi is 3.14, and then so 2 pi is 6.28. So that's what we just did. We figured out the linear speed, converted it to how long it's going to take to go around. We used the how long it's going to take to go around to get our angular speed. Multiplying these two together should give us 2 pi. I hope that all makes kind of sense there.
How'd you get 44.9 seconds again?
I did 100 pi divided by 7.
Okay.
Yeah. Okay, so now we have a new angle. We have a new angle. We have a new variable in here, don't we? And we know how fast that theta is changing, don't we? That theta, d theta dt, is, what is that rate of change of that angle? 7 over 50 radians per second. So that's quite a bit of work. It's quite a bit of work to get that. This is one of the more difficult problems. Can you see why? And we haven't even really hit the messy part yet. I mean, this is the messy part, I guess, but there's another part. We clear? I know how fast theta is changing. I want to know how fast r is changing. So now what I need is a formula that connects theta and r together, and you can't participate, Hugo, sorry. So we need a formula that connects theta and r together, and we need to be looking at this picture right here. So can you think of any formulas out there that would connect theta and r together in that picture? And yeah, you might need to refer to something from your formula sheet. Law of cosines. Very good. Let's see why law of cosines will work. Let me draw this triangle over here. First thing I want to point out is that this triangle is not a right triangle, right? So you cannot use anything that has right triangle stuff in it. It's not a right triangle. Now, it is a right triangle at one point in time when this is straight up, right? But otherwise, it's not, so we can't. But we have a law of cosines. And the law of cosines works like this. If you have an arbitrary triangle, and we call this A, little a, B, little b, C, little c, then law of cosines says, there's three versions of it, of the law of cosines. But basically it says c squared equals a squared plus b squared minus 2ab cosine c. That's one of the formulas. Then you could have a squared equals b squared plus c squared minus 2bc, whatever, anyway. You can just switch the letters around. Does that look familiar from pre-cal? Okay. The thing that's good about this law of cosines is that it includes an angle, right? And then everything else in it has to do with two sides of the two other sides of the triangle. In other words, if we look at this formula right here, this little c, or sorry, the c is in there, right? And then the a and the b are in there. And then the little c, this is the opposite side, right? Like that. Those are the things that are included in that formula. And if you look at our picture, if we look at our angle theta here, law of cosines is going to work with this side, and that side, right? And that should connect all of those things together. Now the good news is that two of the sides are constants, aren't they? So let's try and write the law of cosines formula using that picture instead of this one. So what would it be? What would you want to use for little c here? That's going to be our little r. So it's going to be r squared equals then a, we could use the 50. Let's just go 50 squared plus b squared, which is 100 squared, minus 2 times 50 times 100 times cosine of, nope, can't hold it constant yet, right? It can't, it's just going to be cosine theta. That's our equation. Now Sophia kind of helped us by getting that. I'm not sure how Sophia got that. I mean, I can't really teach that part of it, you know. You either kind of know where to pull from or you don't, you know. And so you might have to fumble around with some formulas for a while trying to figure out what works. But you can see how that might be challenging. Now, law of sines might have been something that you might have been thinking of, but the problem with law of sines is that law of sines, it uses two sides and two angles. So like law of sines is this, sine capital A over little a is sine capital B over little b. And the problem with this is that it requires two of the angles, and we only have one angle. We don't have two of the angles, and we don't want to start incorporating another variable in there. So the law of cosines is perfect for this situation. So we needed our equation, right? There it is. I'll put it right here. Here's the equation we needed. And what's the next step?
Find out what theta is 120. Or r is
Take the derivative.
Not quite. That'll come. But the next step is the derivative. You need to take your derivative now. So we're going to differentiate this equation. Remember, the whole point of coming up with that equation is that now when we differentiate it, we should get what to pop out of it? dr dt and d theta dt. They should both pop out of this equation, shouldn't they? And here's the equation. I've got a lot of constants in here, so I'm pretty happy when it comes to this derivative. Y'all ready for it? Okay, so I'm just going to put here, I'm going to write derivative even though I normally don't write that. Derivative. All right, what's derivative of r squared? 2r times dr dt equals derivative of 50 squared, 0. It's a constant by itself. Plus derivative of 100 squared, 0. Minus, now look at all of these constants are attached to this, so they have to be included. So what is that? 2 times 50 is 100 times 100. So negative 10,000. Negative 10,000 is going to come for the ride. What is the derivative of cosine of theta? Negative sine of theta. So I'm going to put this in parentheses. Negative sine of theta d theta dt. That is that other part you have to be aware of. When you take derivative of cosine theta, you take derivative of cosine first, you get negative sine, but then you have to go inside chain rule and take derivative of theta with respect to time, which is d theta dt. And that is it, right? Clean this up a little bit. R dr dt equals 5,000 sine theta d theta dt. So the two negatives here made it a positive, and I divided both sides by 2 to get rid of that 2 on the other side. Turn the 10,000 into 5,000. We agree? All right. That's it. This is the equation we're going to work with right here. Now let's go through and check to see what we have, and we're probably going to have to go grab some information. D theta dt I know is this, right?
Yeah.
So this part I've got, check. Dr dt is actually check because that's what I'm solving for, right? And then what about r? Do I know r? Yes, I can actually freeze everything in time now. R is going to be 120. That's good. The only thing I don't have is this. Right? I don't know what theta is. But I can freeze everything in time now, can't I? All right, so if I'm going to freeze everything in time, I can come back in here, right? I can freeze everything, which means I come back to this equation. I replace r with what? 120. And I can solve for this theta now. It's the only variable left in here. Understand what I'm doing? Okay, so let's go ahead and solve that. I'm going to erase some of this. My intention for the next exam is to put maybe I'm going to have like 2 or 3 of these challenging ones, but I'm going to give them as take-homes. All right? Just because they take too much time. I mean, look, we're 40 minutes in here. All right? All right, so let's go ahead and do this. I'm going to do 120 squared minus 50 squared minus 100 squared all over 2 times 50 over negative 2 times 50 times 100 equals cosine theta. So all I did here was brought these two over, which made them subtraction. And then I divided by negative 2 times 50 times 100, and that left me with cosine theta. Now I'm going to get my calculator. I'm going to go ahead and compute all this first, figure out what this is. Okay, so in the numerator I'm getting 1900. And in the denominator, didn't we already say that was negative 10,000? We good? So now 19 divided by 10,000 and get a decimal here, negative 0.19 equals cosine theta. Now what? Arc cosine both sides, inverse cosine. And you need to pay attention to what mode you're in your calculator. Okay, so I happen to be in degree mode. I'm going to do arc cosine of negative 0.19, and I get 100 100.95 degrees is theta. Don't understand what I did here? Inverse cosine on both sides. You get this? Now, I needed to know what sine of theta was, right? I know what theta is. It's 100.95 degrees. We're almost there. You all look thrilled. Yeah, I put the degree symbol there. Now, if you're in radian mode, you're going to get a different answer. That's okay. Just make sure you know you're in radian mode. All right. Here we go. We should be really close to the answer here. I'm going to rewrite this equation. I'm going to replace everything now. R is 120. dr dt was dr dt, that's what I'm solving for, equals 5,000 times sine of 100.95 degrees, which I'll use my calculator for, times d theta dt, which was 7/50. All right, so I'm going to do that, that. And then, you know what? I'll just divide all that by 120 when I'm done.
Sir,
Yes?
is it okay that like theta is in degrees and 7/50 is radians? You know what I mean?
Yes, because sine of the angle is just a number. Okay? That's why it doesn't matter. If you were to have done this part right here in radian mode on your calculator, you would get an answer in radians. But then you're going to take sine of it, and it's going to spit back a number between -1 and 1, right? Because that's the range of sine. All right, so here I go. I'm going to do all this on my calculator. Times sine of 100.95 times 7 divided by 50 divided by 120. Anybody have it yet? I'm getting 5.7-ish. Okay, close. 5.73 maybe. What? 5.73 what? Meters per second. Remember, R was that length, the distance between the observer and the runner. And that was growing like a line, so that's going to be meters per second. Think about this answer. Are we confident that does that answer make sense? Why or why not does that answer make sense? Let's say that I'm watching this person run, right? And I've got a rope attached to them. And instead of them running around a circle, they start running straight away from me. How fast is that rope coming out of my hand? 7 meters per second. It's never going to get any faster than that, right? But this person's running around a circle, right? So some of their velocity is going up, not directly away from me, right, as they go around the arc. So my answer should not be bigger than 7. Do you agree? So I'm feeling really good about this. Yeah? That's the answer. That's how fast the rope is coming out of that person's hand. If they were tethered together, that's how fast it's coming out of their hand at that particular instant. Now, you could think about something like, instead of doing this, if you have, you can imagine, I think we talked a little bit about this, if you have like a piston and an engine attached to a crankshaft, and you've got this crankshaft turning, and you've got the piston moving in the cylinder, you can start to, this would be more complicated, all right? But you could say, if this piston is moving at a certain speed, then how fast is this point going around the circle, right? You can figure out, you know, what is the revolutions per minute, or, you know, exactly at a certain point in time, how fast is this point moving? This could all be tied into something more complicated. Does that make sense? The runner around the track is just to kind of get us thinking, you know. All right. I think that's good. Are y'all done with related rates? I'm ready to start the next thing. So I will supply you with some take-home problems. And I plan on doing that pretty soon. I don't think I'm going to wait for the next test. So what will happen is when I give you those problems, I'll give you whatever it is, maybe a week, and you'll have to turn them in. And that will be, the grade on that will be kind of held in reserve until the next test, and that will be a certain percentage of the grade. Okay? Now, because it's take-home, I expect to see original work. Do you know what that means? Your work, not the tutor in the tutoring lab. So if this has happened before, but if I find out that you worked with somebody, then your penalty is to be dropped from the class. So I really do mean you have to work alone on it. But we'll talk more about that when I hand it out. Okay, chapter 3, inverse functions. This seems weird. All of a sudden we're going to start talking about inverse functions. This is like a college algebra topic. Let's take a look at this chapter. Exponential functions. Did that in college algebra. Inverse functions and logarithms. Did that in college algebra. 3.3 is where it really begins. 3.3 is the derivatives of those functions. So we have very, very carefully avoided all exponential and logarithmic functions up to this point. We've only done polynomials, rational functions, trig functions, right? Derivatives. But we haven't talked about what's the derivative of an exponential function. We haven't talked about derivatives of logs. So we are going to do that, but I'm going to do a quick review of exponential and log functions. And then we'll talk about inverse trigonometric functions, because you did those in pre-cal. And what are the derivatives of those? And then we'll introduce these things called hyperbolic functions, which you have not done. And then what are the derivatives of those? And then we get to this very, very nice section, the indeterminate forms and what's called L'Hopital's rule. It looks like La Hospital, but it's L'Hopital. And this section is a very important section right here, 3.7. Very important section. All right, so let's do a quick review of exponential and log functions. I even say we're going to go quickly through this. So I really do hope that you remember what an exponential function looks like. This is what an exponential function looks like. Let's take a look at some of its behavior. It has a horizontal, and I should state here, this is the function that we're looking at there, f of x equals a to the x, where a is bigger than 0 and a is not equal to 1. This is the way that we define exponential functions back in college algebra. So you have your variables up in the exponent, and your base is a number. This number can be any number as long as it's positive and it's not 1. So some examples of exponential functions are things like 2 to the x, right? Okay, you could have another one, 5 to the x, 10 to the x. You could have e to the x, right? That's that real nice, that special one. So these are all exponential functions. As long as if this number right here, a, is bigger than 1, so all of these, this is what it's going to look like. It's going to be what we call exponential growth. So as you move from left to right, the graph grows. As you go out to infinity, your graph goes up to infinity, right? But as you go to the left, as you go to negative infinity, your graph actually comes down and approaches what? 0. Okay, so that's what this is saying. The limit as x goes to infinity of the function. Hold on a second. Make this a little bigger. A little bigger. There we go. That better? So as the limit as x goes to infinity of this function is infinity. As we go to infinity, it goes to infinity. As we go to negative infinity, the function goes to 0. Yes? Now, that's if a is bigger than 1. That's if this number is bigger than 1. If we make that number smaller than 1, but still positive. So like 1/2, or like 1/5, or like 0.7. As long as the number is smaller than 1, it's going to do something else, right? If a is less than 1, it decays. All right, so here's the picture if a is less than 1. It basically just flips it over. Okay? It's like a reflection over the y-axis. Does this kind of look familiar?
That's the derivative?
Nope, we are not doing any derivatives yet. That's just the function itself. So this is exponential decay. So now if you take the limit as you go to negative infinity, the function goes to positive infinity. As you go to positive infinity, the function goes to 0. Yes? Those are your basic exponential functions. Now, remember some things about exponents. We'll need this later. These exponent rules, that if you have something to a power times something to a different power, same base, you add the powers. If you have division, you subtract the powers. If you have something to a power, you multiply the powers. These are all like pre-algebra properties. If you have two things being raised to a power and they're being multiplied, you can apply the power to each one. That's all I have for exponential functions. That is quick. I will add one more thing on there, and that's the, recall the natural exponential function. And that was that very special function, e to the x. So e is a number, right? It's approximately 2.718, but it goes on forever. It's what we refer to as a non-repeating, non-terminating decimal. It's an irrational number, just like the number pi. All right, so this is one of those things where it just keeps going. There's no pattern to it. It just keeps changing. And that very special number raised to the x, that is positive, right? That's a positive number. It's bigger than 1, so this should be some sort of exponential growth. We will talk about what's so special about that natural exponential function, but I know you saw that in college algebra, right? And we never really explained there why that's so special, but we'll talk about it today. All right, let's talk about inverse functions. Be sure you review this college algebra topic, especially inverse function. For now, I focus on the main aspects of logarithmic functions. So just remember, when it comes to inverses, do y'all remember how an inverse function works? Let me give myself some room here. So if you have a function, this was the picture that we used back when we were first talking about functions. Y'all remember that picture right there? Okay, so this, you have some function f. Here we have what's called the domain of f. I'm put dom f. These are the things that are allowed to be plugged into this function. Some functions have restricted domains, like, for example, square root of x. You cannot plug in negative numbers, right? So the domain of this would just be like 0 and then all the positive numbers. But the things that can go into f, that's its domain, the range, which I'll call ran f, the range is the output. Okay? And when it comes to an inverse function, what the inverse function does is it undoes that function. So it takes everything back to where it came from. So the picture of the inverse goes like this. It goes from here backwards to here, and we use the little negative one with notation for the inverse. And therefore, the domain of the inverse function is the range of the f function, and then the range of the inverse function is the domain of the f function. So the domain and ranges switch places. Okay. We also have this property with inverse functions. If you take a function f and you compose it with its inverse, then it spits back x. And it also works the other way. Do you all remember seeing that in college algebra? That those two properties had to hold to be able to talk about an inverse? That these two things had to be true? Now, here's what's happening in the picture. Let's do this in the picture. Let's say I start out with an x in here, okay? When it comes over here, that will be f of x, won't it? And then when I take it back through this one, that's f inverse of f of x. So it's like first x goes through and has f does something to it, right? That answer, f inverse does something to it and sends it back. Well, where does it have to go back to? X. It has to go exactly back to where it came from. That's what this is saying. If x goes into f first and then that goes into the inverse, it should just come out where it came from. And it works both directions. If you start with an x here, go here, and then back, it should go back to x. All right, that's just a very quick little reminder of how inverses worked. Now, I talked about inverses real quick because we're about to discuss logarithms. Okay, so when we talk about logarithms, if we have a function that looks like this, that was called a logarithmic function. And the restrictions we had were, again, that a had to be positive and a could not be 1. So you could replace this right here. This is called the base of the logarithmic function. You could replace it with any positive number except for 1. So you could have like log base 2, log base 5, log base 10. You could even have fractions in there, log base 1/2. And when you graph them, that's what it looks like if a is bigger than 1. So this picture right here is a log function with a bigger than 1. Let's talk about the behavior of this. I'm not quite sure. This slips through the cracks. I don't know how it does, but I will stress this as much as I can. This is your basic logarithmic function, right? With base bigger than 1. As x goes to infinity, where does this function go? It goes to infinity. Now, it doesn't grow as fast as an exponential function, but it does grow. So if I continue going out here, I'm going to continue going up and up and up, and it's going to go to infinity. All right? Just slowly, but it will go. Now, here's the thing about logs. I cannot go to negative infinity because there's a domain restriction on logs. This is the y-axis. You cannot plug a negative into a log. Do you remember that from college algebra? If you type it in your calculator right now, try and do log of a negative number, it's going to give you an error. That's because you can't plug negatives into logs. All right? So we can't talk about going to negative infinity. What we can talk about is what happens as we approach 0. So what happens is I start to go towards 0. Where is the function headed? Negative infinity. And that's what this is saying. The limit as x approaches 0 from the right, from this side, of the function is negative infinity. Do not forget that, all right? I don't know, that's what I'm saying. Students always forget this fact right here. As you approach 0 from the right on a logarithmic function, it drops to negative infinity, all right? See it in the picture? Okay. Now, what happens if I switch it and I make this a less than 1? It goes like that, okay? So now, as you go to positive infinity, the function goes to negative infinity. As you approach 0 from the left, it goes to positive infinity. I don't know why I don't have it here. So let me put it up here real quick. If I were to ask you to graph the function f of x equals 2 to the x, that is an exponential